just in case. And then we will pick up where we left off. So I have the note here to start. Let me see. Let me make sure you can hear me. I'm sharing my screen and then I'm recording. Okay. Okay. So here we're looking at the limiting reactant, the one that we know that it runs out first. The one that we know controls the amount of product made because it runs out, and as soon as it runs out, the reaction stops, right? The limiting reactant in theoretical yield problems. So we're looking at this, and this is one of those conceptual problems. So conceptual problems don't really have a lot of math in them. They're usually more, I was about to say conceptual, they're usually more word problems or kind of what appears like puzzle pieces, right? You're trying to solve a problem, but you don't have to use a lot of complicated math to solve it. Okay, we're looking at nitrogen and hydrogen gas reacts to form ammonia according to the reaction below. So the nitrogen gas and the hydrogen gas are reacting to form ammonia. If a flask contains a mixture of reactants represented by the image on the right, so this is the flask right here on the right. Which image below best represents the mixture in the flask after the reactants reach as completely as after the reactants have reacted as completely as possible? Which is the limiting reactant, which is the excess reactant, or which is the reactant in excess? Okay, so here's the thing. Before we look at the picture, we have to understand what the balanced equation is communicating to us. The balanced equation tells us the kind of interaction, right? It kind of gives us a preview of what to expect. So the way things work in the scientific process is we usually have a hypothesis based on some kind of experience. Oops, I'm using my hand a lot. Based on some kind of experience or knowledge or research, we have a hypothesis. So we kind of jump ahead and make a judgment, right? And that's part of the scientific process. And the judgment that we make, it's kind of like a prejudgment. Oh, based on what I just heard, I think this is what's going to work out. That prejudgment is our hypothesis. And what the hypothesis provides us with is kind of a template of what to expect going into the experiment. And then when we go to the experiment, in that scenario, we're testing our hypothesis to see if it works out or not. The balanced equation is stronger than a hypothesis. The balanced equation tells us how these reactants, when they're put together, are going to react. So we go in there and we have an expectation based on what the balanced equation said. It provides us with a guideline. Okay, when nitrogen and hydrogen get together, it shows here one. So you see the coefficient is 1. The coefficient is a multiplier used to balance the equation. It shows us here from the balance equation, every 1 molecule of nitrogen needs or must react with 3. So there has to be 3 available hydrogens to react with nitrogen. So from here, let me see if I can add a page. So once we understand what the balance equation is telling us, then we know how to read or solve this problem. Okay, so I'm going to use the units of measurement, which is moles. So every 1 mole of N2 that reacts needs to be complete, to be stoichiometrically complete, needs 3 moles of H2. Okay, so it's kind of like a missing piece based on the balanced equation. When you have 1 mole of N2, you need 3 moles of H2. And then when they come together, what happens then? To produce 2 moles of NH3. Okay, so the balanced equation is telling us this. Now remember, the mole represents amount, right? You could have said molecule, but we get the amount. The relationship is for every 1 of this, we have 3 of this to make 2 of this. Okay, now we have to relate this to the picture, right? N2 will be 2 circles stuck together. So I'm going to draw a picture here. N2 will be 2 circles stuck together because that's what the N2 molecule is two of the same nitrogen atom. H2, I'm going to use a different color here. Let me use green. Will be three of these, right? So it's H2, so they're stuck together. So every time we have one and two, we need three H2s, right? So let me not write the three there because it sounds like it's 3 times 3, which is 9. But you get the idea, right? These are 3. I write on the bottom. 3 here, that's the count on the bottom. And the count on the other one is going to be 1. Oh my goodness, I'm typing the wrong thing. Yeah. So when these come together, they make a product. And so before I look at the picture, I'm trying to make sense of it here before I look at the picture. So I made N blue, right? So in the product here, we end up with 2 of these. Let's see. Oh, I only have 2 blue circles anyway. So here's one blue circle, here's another blue circle. Okay. In this formula here, it shows that one N is surrounded by 3 H. So I drew the N's separated because they get separated in the product. And then each N has to have 3 H's. So H's are represented by green colors, right? So I'm going to write 1, 2, 3. 1, 2, 3. Okay. How many H's did I have? Like individual H's, not H2s. If I count the individual H's, 1, 2, 3, 4, 5, 6. So I see here, 3 H2s had 6 individual H's. So hopefully you can see that. And then when I say I have N2, that's the same thing as having 2 individual N's, right? Remember, each circle represents the element, and the element is the atom. So here, I use everything I had available, and I get this product. Now that I get how it's supposed to look or the idea of it, let me look in the picture and see. They're saying, oh, this is the beginning, right? They said in the dialogue, this is what the reactants are. So in the reactants here, I know H2 and N2 have to react to produce a product. So let me see how many combinations can be made. The product is going to be, these are the reactants, right? The product is going to be NH3. I know that from the balanced equation. They already told me what's going to be made, NH3. Now, this one is saying if you only have one NH2, you have the ability to make 2 NH3s. As long as you have 3, you also have 3 H2s, right? So let me see how many NH3s I can make from the combination I have here. I know each NH3 has to have 1 nitrogen and 3 hydrogens, right? The nitrogen is what color? Blue. So I'm going to stick with blue color. So I have 1, 2, 3, 4. So it looks like I should be able to make 4 NH3s, right? Do I have enough H's to make that? Let's see. 1, 2, 3, 4, right? I have 4 N's, so I should be able to make 4 NH3s. Let's see. Right now, I have used or separated all the N's. They're ready to go. I need to add 3 H's each time. What color do I use for H? I guess I'll stick with what I had before. H's here will be green for my case. Each of the N's need 3 H's. 1, 2, 3, right? 1, 2, 3. Once I'm done using the H's, I'll check to see if I had enough. 1, 2, 3, 1, 2, 3. Okay, 1, 2, 3. Okay, so let me see. For the 4 N's I end up using, I needed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I needed 12 H's. So I end up with 4 N's, not N2s, right? And then 12 H's. But when you look at them as diatomic, this ends up being 2 and 2, and then 6 H2, right? Because remember, in the reactant form, the nitrogens are not existing as monoatomic. They are diatomic, meaning they are together. So you're kind of getting double each time. Okay, so I essentially use all 2 of the nitrogens, and I use 6 of the hydrogens. Do I have enough? Do I have 6 hydrogens? 1, 2, 3, 4, 5, 6. Oh, I had more than enough. Well, what about these 2? So, oh, I forgot. I'm getting so caught up in this illustration. They said, which of these flasks shows your product? I know that I have to make 4 NH3s, right? Which one has got 4 NH3? Let me see. They said this is here. The one with the big blue circle and then the three white circles, that's NH3. I have one, I have two. Oh, so it's not A. I need to get to 4. Okay. This one, I have 1, 2, 3, 4. This looks good. But did you see here when I said I use 6 of the available 8 H2s? So there is 2 H2s that don't get used at all. There's an H2 here, and there's an H2 here that doesn't get used. They're not asked. So I would say this is a possibility. Move over here. Ah, this is much better. It shows me my products, my 4 NH3s right there, there. And it shows me my extra H2s used. So C shows me the whole picture that's happening. I am going to make 4 NH3s like I just showed you in the picture right here. But I'm also going to have 2 H2s that did not have anything to react with. Okay? So C should be my answer. So based on that, C will be my answer for the first part. Which is the limiting reactant? That would be N2 because I could have made more NH3s if I just had more N2, but my N2 ran out. Then which is excess? H2. They're not asking you how much, right? So yeah, I could have made I had what is it called? H2 and more, but I just ran out of the N. So by virtue of that, N is limiting, H2 is excess. That you have to learn in this class that you have to reach, this is a goal, so you have to reach, is being able to use a picture like that, a particulate level. So this is called particulate level or molecular diagram. So molecular diagram or particulate level, particulate level diagram. It's just showing you what is going on in the balance equation from the view of the particles, the molecules and stuff. So now that we see that, we can then move on. So once again, they define the terms, summary. The limiting reactant or reagent is the reactant that's completely consumed in the chemical reaction. We just saw it play out, right? It ran out completely. I was out of it once I made products in the chemical reaction. And limits the amount of product. So the limiting reactant, because it runs out, even though the other excess reactant is present, you can't make any more product. So we just saw that. The reactant in excess is any reactant that occurs in a quantity greater than what is needed or required to completely react with the limiting reactant. The balance equation tells us how much of each reactant is required, right? In our case, we saw 1 for 3, but we end up having more than what the nitrogen needed. So it made hydrogen an excess reactant. The theoretical yield is the amount of product that can be made in a chemical reaction based on the amount of limiting reactant. Remember, the reaction goes on as long as you have the limiting reactant present. Once the limiting reactant ends, the show is over. The reaction is over. Everybody goes home, and whatever product you have is what you were able to make, right? And then once the limiting reactant is made, this is called a theoretical yield. What is the actual yield or experimental yield? This is the amount of product that you actually produce by a chemical reaction. This is referring to in a lab. A theoretical yield is what you can produce. That's the amount that can be made, assuming everything in the lab goes perfectly. You know, you're experiencing working in a wet lab, so you know that sometimes you make mistakes, and if you're making a mistake, you're most likely not going to get a theoretical yield, because theoretical yield assumes perfection. Everything, the chemicals are perfect amounts, not necessarily, I shouldn't say perfect amounts, but perfect condition. They don't have any impurities. The chemical process is done perfectly, and then after all, everything is perfect, you get exactly what you were supposed to get, and that will be the theoretical yield. But the actual yield is when reality sits in. You go to the lab and then you realize, oh, Your supplies are a little bit dirty. You don't have enough of them. There's some impurities. Your glassware is messed up. You're having an off day. Life happens in the actual, and then you end up having less than, right? You end up having less amount than expected. Okay? So to judge, the percent yield is a way for us to judge, were you able to reach that theoretical yield? So theoretical yield is that scenario where everything is perfect. Were you able to get to that theoretical yield? We don't know. So we take your actual yield, what actually happened, right? And divide it by the theoretical yield, what we wanted to happen, and multiply by 100. If you get 100%, then you're saying that you had a perfect day. Everything worked out the way you planned. You had no issues, no errors, no spilling of sample because everything was perfect. But if you have less than 100%, then you're saying, yeah, life happened. And if you have maybe let's say 105, there's an issue here. It's impossible to make more than 100% because the theoretical yield, the other definition for this is the maximum amount you can ever make is that theoretical yield. So that in reality, there's no way for the actual yield to be bigger than theoretical yield because that's the maximum amount, right? This is the maximum amount. So people sometimes in the lab get more than 100%. I have done that in my organic class. Well, what was I doing? You get impatient, youth. I had places to go and places to be and things to do, right? I lived in school, hashtag dorm life. There wasn't hashtag back then. This is way back then. Anyway, so I was being impatient. Then my GA, the guy who was watching us, so our professor did not teach the labs. The guy who was watching us, he's like, "You work so slow," talking about me. Move faster. And I'm like, I want everything to be perfect because I was trying to hit that. I was trying to get theoretical yield, okay? And I was moving so slow to make sure I got every grain. But when I got my sample was wet and I had to dry it. Because he was rushing me sometimes, and sometimes I was just getting impatient, I would take my sample while it's still wet. And when you have a hundred or higher than 100%, not 100, but higher than 100%, it's usually two possibilities. If it's higher than 100, either your sample is wet, so you're weighing water, or you have some kind of impurity. If your chemicals were not pure and they were dirty, or you use low quality samples, you're getting your actual yield plus some contaminant. Maybe you're sloppy, you drop something in there, a little bit carelessness, but you have what you want plus something else. Okay, so just FYI. So let's move on. Now we're going to be doing some problems. Ooh, okay. In this problem here, we're told ammonia NH3 can be synthesized by the following reaction. So now we're making the same compound ammonia. Let me add a page down here because we're going to be using some math to solve for our problem. So I'm going to write my balanced equation because stoichiometry, we're still working on that, begins with our balanced equation. We're going to be doing mass to mass, it looks like. I think we're going to be doing mass to mass. Yep. Okay. So I'm going to do this. Let me write the mass to mass conversion path. Okay. So the mass to mass conversion path, mass to mass. This means your given is a mass. Your wanted is also a mass. So you're starting from a given to a wanted. This is the path. I'm going to draw it on the right. I'm going to illustrate it on the right. We start from grams of given. We convert to moles of given. Do I have enough space? We'll see. And then we go to moles. Oh, moles of wanted. I'm going to write this in the bottom because I can tell I'm writing on a space. And from there we go to mass. I say gram of wanted. So as I focus on this, we start from grams of given. We go to moles of given. We go and then end up on grams of wanted. So memorizing this, okay, I can memorize patterns. But it was harder for me to memorize. But when they're connected in the pattern, For some reason, my brain is like, we can do that. Let's memorize the pattern. So the pattern I see here is G, MOL, MOL, G. So like a palindrome, right? And if you look at this, it's kind of like the left side is sort of a mirror image of the right side, right? You go from G to M to M to G, right? So it goes like this: G to M to M to G, like that. If you remove the details out, okay? So we start from grams, and then the first half of the conversion focuses on the given formula, the formula that you're given, the amount you're given. The second half of the conversion focuses on the wanted. So this was the logic I used to remember this pathway, okay? Okay, let's see what is given. So now that I know what the path is, let's see what's given. I'm told starting with 86.3 grams of NO. So, oh, this is my given, 86.3 grams of NO. And I'm given two givens, 25.6 grams of H2, 25.6 grams of H2. And they're telling me find the theoretical yield of ammonia in grams. It's important for them to tell me what the units is, because if I start with grams, I'm starting here. But if they tell me go all the way to grams, I go from there to there, second stop, from there to there, third stop, from there to there, fourth stop. Okay? I end up at grams. If they say end up at moles, I go 1, 2, and I end up here. But they said go all the way to grams, so I have to go from given grams and go all the way to wanted grams. But here's the other issue. They gave me two givens. So first of all, if this is given, this is given, how do I know which is given, which is my true given? Just since you have two givens, label the first one given 1, the second one given 2. So you can separate it. That's it. And they want you to figure out how much ammonia. This is ammonia right here. The other one is water. So what is wanted is the amount of ammonia in grams. Okay? Okay. So what do we do now? We're going to do, remember, for stoichiometry, we only need two formulas, one given, one wanted. But what do you do when you have two givens? Split it up. So we're going to do our first stoichiometry with given 1 all the way to our wanted. Then we'll make our stoichiometry again with given 2 all the way with wanted. Because remember I told you, the stoichiometry path that we use only requires two players, the given and the wanted. So you cannot combine both givens in one equation. I've seen students do funny things. I'm like, y'all, one given. So since you have more than one given, split up the work and then do the work twice, each time with one of the two givens, right? So our first stoichiometry, we start with the first given. So I'm just going to show you where it's going, right? It's going to involve these two reactants, these two players right here, that and this, okay, for my first path. So I'll start with the given number, this one here, 86.3 grams. And what's the formula here? NO. Oops, it's not that the word no, it's N big O. And then I'm going to write my PT. Oh, I forgot to mention this before. Don't forget, it's PT, BE, PT. This is a reminder to you of where we get the conversions from. So PT is what? PT periodic table, right? This is always the 1 mole of that formula, NO. And then we're going to write the grams on the bottom here. So the units match, grams of NO. So what's the grams of NO? I wrote this too close. We're going to do G2 to wanted down here. What's the mass of NO from the periodic table, right? That's what I'm trying to get right here. N is what? What's my periodic table? Yeah, N is 14. O is 16. I'm writing approximate numbers, right? So when I add these two, I get 30. So this is going to be 30 grams. That's what the PT is here for, to remind you where you get or where you look to get the answers. Or not the answers, but the numbers. Then we do BE here, balanced equation. In balanced equation, let me see. I'm working with these two. This moles here, those moles there. So remember, the units up, oops, I keep forgetting what setting I have. The units I have here, grams of NO, have to match the units on the bottom. I know I'm saying a lot, but we are building up, we're scaffolding, that's what they call it in education needs. We are building up on what we learned before. So that part, dimensional analysis should not be new. We've used it before, we're just using it here again. We're using it in a different context, but we're using it here nonetheless. So that part should not be new. Units must match diagonally. So if this unit up here is mole of NO, then down here, the unit should also be mole of NO. But here, I look at the balance equation. What's the mole in front of NO? It's 2. So I write 2 here. And then the other formula, the wanted, the formula is NH3, and we want its mole also. What's the NH3 mole? Is also 2 from the balance equation. Then I move on. I'm done with my balance equation. I'm back to my periodic table because it's PTBEPT. Okay, with my periodic table, let's see. Let me cancel out the units as I set this up. Now, I want the mole of NH3 to be on the bottom, and then up here I'll write grams of NH3. Okay, so mole of NH3 on the bottom, grams of NH3 on top. Okay, so here I'm going to write 1 mole of NH3. And up here, let's see, grams of NH3. Oh, N is 14. Then I have 3 H's. Each H is 1. So it's just 17 grams. 17 grams. Okay. Mole of NH3 cancels out with mole of NH3. When I work out my math, the units that remains is going to be the units of my answer. Grams of NH3. Right? What are the grams? Okay. We're going to multiply everything on top, which would be 86.3 times 2 times 17. Divide by everything on the bottom. 30 divided by 2. So what do we get? My calculator here. I don't know why I do work in the dark and I can't see very well. It's a tragedy. 86.3 times 2 times 17 divided by 30 divided by 2. What do we get? 48.9. So this is going to be 48.9 grams of NH3. Okay? So you see that. I don't like the numbers being on a different page, but yeah, you see that. 48.9 or different level grams of NH3. That's our answer. Okay? Our answer for that G1 to W. So what we're saying here is, before I go to G2 to W, if 86.3 grams of NO completely, all of it completely reacts, comma, 48.9 grams of NH3 will be produced for sure. Okay? But this is only half of the story. They said find out which of these reactants is the limiting reactant. Well, they didn't really say that. That's what I'm thinking. They said find the theoretical yield of ammonia. And I'll show you how we do that once we're done with the second part. We're now going G2 to wanted. We're trying to figure out if, so I'm going to use a green, sorry, I'm saying green, I wrote blue. Let me change this so we're completely dealing with blue. G2 to wanted. What if this time the amount that's reacting is the H2? If that's the limiting part. So we're trying to play out a scenario. The first scenario we try to play out is if NO is a limiting reactant. That means all the limiting reactants completely reacts. Second scenario we're examining is if H2 is a limiting reactant. So when we're saying H2 is reacting, we don't mean it's reacting with itself. It's implied it's reacting with the other reagent, but we are assuming it's completely reacting. Okay? So G2 and W. So for that to work out, let me see. My starting amount is 25.6. I have to zoom on so I can see the numbers. So 25.6 grams of H2 react. So in this case here, what we're trying to say is assume hydrogen is the limiting reactant. So all of it has to react. If that's the case, then what happens? So we're going to do again PT, right, in our conversion, BE, just like we did up here, and then PT. Well, we don't need that much space for a balanced equation. And then PT. I think we can use up the space we have. Okay. So this time our given 2 is hydrogen. So as usual, we have to do 1 mole of hydrogen, right? The units across must match. So grams of H2 has to be here. Let me go through and just write the units. Then on the bottom here, mole of H2, right? For BE, that goes with this right side. Mole of NH3. Okay, I'm not writing the actual numbers. Then down here, we have to have mole of NH3. Then on top, we have grams of NH3. Okay, so I wanted to show you how the units work out. You can put that in before you even put in the numbers. Okay, so you can see this unit matches with that unit, that with that, this with that, and then the last one doesn't match with anything. That's why it remains. Okay, now the actual numbers. What's the gram from the periodic table of 2 H's? Each H is 1, so times 2, we have 2 grams here. Done. Look at the balanced equation. What's the moles in front of H2? Let me look at the balanced equation. Oh, H2, 5. NO2. Wait, sorry. Why am I going to NO? Oh, come on. H2, 5, right? Because that's what you see why I draw this path here, because I get very distracted. All this stuff I wrote here is distracting me. H2 is 5, NH3 is 2. So I'm using these right here. These right here, 5 and 2. That's why I have the colors there so I can see. Okay, 5 for H2, and then 2, right? 2 for NH3. I should have rewritten the balance equation down here so I'm not going up and down so much. Okay, remember the moles in PT is always 1 mole, like we have here, always 1 mole. We don't look at the balance equation to figure out what this is. And then the grams of NH3, the grams here of NH3 from the periodic table is, let's see, N, which is 14, and then H, which is 1 each times 3. This is going to be 17. Okay, please notice when you're working on this, as a student, since I had to work on a bunch of these when I was working on them to really get the hang of it, which I would encourage you to do that, I started to notice, wait a minute, when I'm doing the 2 givens, look at what part is similar. See, this top part to the bottom part right here is just like this part here, right? And I'm like, oh, I don't have to even work hard over there. I can coast all the way to the end. Okay, now let's do our math to figure out how much of the NH3 gets made. Okay, 25.6 times 1 times 2 times 17 divided by 2 divided by 5. Okay, 25.6 times 1 times 2 times 17 divided by 2 divided by 5. 87.04 grams of NH3. Aha. So here's the thing. So what we're saying, if H2 completely reacts, right? And if it's completely reacting, then we're saying that it's a limiting reagent. If it's a limit, I should say that's kind of a conclusion. If it is a limiting reagent, because the limiting reagent reagent is the only one that completely reacts. So when we're saying if H2 completely reacts, aka if it is a limiting reagent, right, comma, 87.04 gram of NH3 is formed. Okay, so let me make sure that my masses are correct. They do the math here. 49. Wait, what? Oh, they didn't go all the way to the end. Okay, that's fine. That's fine. Yeah, they did a different method. Okay, so finally, you have to be the judge. Which chemical is the true limiting reagent? Is it NO? Is it H2? Okay, Somewhere back there we said the limiting reagent makes less product. This is where that definition matters. Okay. So the true limiting reagent will make less product. So let's look at our product, 87.04, 48.9. The winner is NO. NO is the true limiting reagent. Why? It makes less product, 48.9 or approximately 49.0 grams. Okay? So here, after doing all this work, we're saying NO is the limiting reagent. We were testing, we are hypothesizing, right? If and then. So if NO was the limiting reagent, this is how it will play out mathematically. If H2 was a limiting reagent, this is how it will play out mathematically. Once you get your result, you judge your result, and then you work back and realize, no, not if, but this is the true limiting reagent. The winner goes to, or the prize goes to NO. That's the limiting reagent. Okay, so while we're here, I want to define something. I want to define extra things or assign extra labels. NO is a limiting reagent. Therefore, H2 is the excess reagent. They didn't ask you all that, but while we're here, H2 is the excess reagent. So just note that by virtue of the answer we got. If one reactant is limiting, the other one is excess. And then this amount here, 49.0, is the theoretical yield of NH3. So the actual amount of NH3 that gets made will be this amount here, 49.0 grams. Okay, so we have seen limiting reagent mathematically. We have seen the excess reagent by default. We have seen the theoretical yield mathematically. So in this one question, we have identified all these three things. Okay, now they just asked us to figure out how much the theoretical yield of ammonia, but we saw this right here is a limiting reagent. This is the excess reagent. And after all our math, the amount of ammonia that got made was 49.0 grams of ammonia. Okay? And we did that by mass to mass. So I'm going to be doing less explaining as I go into the stuff so I can be more streamlined in my process. Yeah, they got this right here. Okay. So I'm trying to see how many more of these do we have to work out for. Oh, this one has an actual yield. Okay, this is this type of reactions. Oh, okay. So let's work this one around here. In this problem here, once again, let me add the page. I should add more than one page. Here's a balanced equation, so I'm going to write this out. Okay, when 28.6 kilograms of carbon react with, oh, so here, I should have copied this better. It's okay. My given here, no, I say it's okay, but it's really not okay. I just want the equation because the stuff that's on top of there is just taking up space I need. Okay, here. I like to make my label once again my given. When 28.6 kilograms of carbon, so here I'm given 28.6 kilogram of carbon, right? Reacts with 88.2 kilograms of titanium 4 oxide. This is it right here. Also, I have two givens. Given 1, given 2 is 88.2 kilograms. 42.8 kilograms of titanium is produced. So here, given 3, what? 42.8 kilograms of titanium are produced. Okay, so they're saying here, find the limiting reactant, okay? In other words, find the one. So our goals here are to, how do I itemize these? Number 1, Find limiting, I'll shorthand it, limiting reagent. This is the one that makes less products, right? So that's my clue, makes less products. Okay, theoretical yield, theoretical yield, that less product that was made, and then percent yield. Okay, percent yield. Okay, so here's the question. When you're looking at this in an exam, right? In a homework scenario, you're not just the homework, but especially the exam is not just, even though the exam is covering 3 chapters, it's not just covering what you just learned. It's covering what you learned and then what you learned before. So you have to study more so your brain can be able to switch as the scenes or the chapters switch. And it took me a while, I would say, in the end in high school is where I really struggled. And then for freshman college, the struggle wasn't as much because I figured out what I had to do to get my brain to keep up with the chapter switching, right? It's fine when we're learning this here and when all we're doing is learning this. It's harder when you're trying to solve this problem on the exam and you just study other chapters. So how are you able to survive that? By studying a lot, right? Okay, so here, back to the question. We have 3 given numbers. So what numbers do we use for what? Do we do 3 conversions, mass to mass? Technically, yes. But here's the thing. I want to change the given 3 because given 3 is technically a different number. This number here, even though it's our third given number, it was given to us for the percent yield. Okay? It took me a while to figure this out. This number here, it wasn't specified, but realize this. The third number that's given to this is actual as actual or experimental because we can't and do this figure out what we'll get from this last number here. The amount of is our experiment. So quickly, I have my given 1, check. I have my given 2, check. Now I have to pick my wanted. What is my wanted? Your wanted has to have the same label as your actual yield chemical. So my wanted is titanium. I am trying to figure out what my wanted is also my theoretical yield. I'm trying to figure out how much of the titanium should be produced so I can compare it against what is actually made in the lab. This is the one that's made in lab. That's why you kind of have to understand these questions in the context of what's happening in the lab, because if you take the question outside of lab, it's very difficult to navigate through it, right? This last number here is the actual yield. If you were to go to the lab and do the experiment, they're saying this is what you would have made, 42.8. But we want to know how much you should have made. What number goes here? We're going to be figuring that out, okay? Okay, the other issue I have, which is not really an issue, it's a small thing. They gave me the masses in kilograms. I want the masses in grams, right? So what I'm going to do here is multiply these numbers by 1,000 real quick. It'll make my math a lot easier. 88.2 times 1,000 to get them in grams. So this is going to be, oops, wrong. Okay, this is going to be 88200 grams. This one here will be times 1,000. 28600 grams, right? I'll make all the numbers as 1,000. It make it, I mean, sorry, grams. It'll make it so much easier for me. So this number here will be 42800 grams, right? I multiply each of these by 1,000. So I'll start doing my conversion with given 1 to my wanted. So given 1 to wanted, let's see. Once again, I like those visuals because they help me. I'm going from here to here, right? Only those two, given 1 to wanted. Okay, my given 1 is going to be 28600 grams of carbon. I start my conversion. PT, which is grams of carbon, and then 1 mole. It's always 1 mole of the formula, carbon. Carbon is 12 grams. Not much math. Then balance equation. I have to look at what carbon is paired with, carbon and titanium. So in here I see my moles of carbon are 2 paired with 1 mole of titanium. Okay, then PT again. PT, let me see, I'm canceling these units out, mole of carbon, mole of carbon. So down here I have mole of titanium and then grams of titanium because the PT conversion always has moles and grams, right? So let me find titanium in my periodic table, and the mass is 47.9. 47.9. Okay, it's 8, but I abbreviated it up to 9. Okay, here. As usual, 28600. Oh, no, clear. What am I doing? 28600 times 47.9 divided by 12 divided by 2. Okay, I got 5708 grams of titanium. I mean, if you want to, you can convert it back to kilograms, and that works. Because I think their answers will be in kilograms. So I'll do that in the end. I don't want to do any extra math right now. I know I'm being lazy like that. Okay, this was my given one to my wanted conversion, right? Now I'm going to do my given two. My given two to wanted conversion. So now I'm going from here all the way to here. So my given two, what's the number I have? 88200. 88200 grams, and this is my formula, TiO2. So I'm going to draw my brackets again. Okay, so PT, BE, PT. Okay, so gram of titanium 4 oxide, and then here I have 1 mole titanium 4 oxide. And then balance equation, mole TiO2, and that goes with what? The mole goes with, this TiO2 goes with Ti. So mole of Ti. I told you towards the end, this one matches, right? Mole of Ti, and then grams of Ti. Okay, now I'm going to fill in the numbers. Ti I know is 47.9. I have this up here. I'm just going to copy it, right? Ti is 47.9. And then 2 oxygen. Each oxygen is 16 plus 16. So I end up with 47.9 plus 16 plus 16. 79.9. I write it as 80. I like to deal with simpler numbers. Don't write out too much, right? Because your homework and exams are going to be multiple choice, but you don't want to run up too much. Well, no, your homework does have some filling up stuff too. So, yeah. Okay. So PT part is done. Mole. Oh yeah. I have to look at the balance equation. What's mole of TiO2? Ooh, coefficient 1. Ti 1 and 1. Okay, 1 and 1. Done with the balance equation. Back to periodic table. Why did I leave the 1 mole here? This is supposed to be 1 mole. 1 mole, 47.9. I'm just copying from up there. Why do the work when it's right here, right? Okay, work this out. 88200 times 47.9 divided by 80. I get 5280.9.8 grams of Ti. Okay, so we have 2 scenarios. Scenario 1 is if given 1 was a limiting reagent, how much of titanium will be made? 57. If given 2 was a limiting reagent, how much of the titanium will be made? 52. Of course, we're talking about thousands, right? So, oh, excuse me, that's so loud. I don't know what's going on out there. Okay, so given 2 makes less titanium, so given 2 is a limiting reagent. Okay, so TiO2 is the limiting reagent, right? Because it makes less titanium. So that's the conclusion from that. But the amount of titanium made is this amount here. So I can say 528, I can round it up, 10 grams of titanium, or I can write it as kilograms. So as kilograms, I have to divide by 1,000. I get 52.8 kilograms, right? One, two, three. Yeah, I moved this 3 times, right? 52.8 kilograms of titanium is produced. Therefore, this is going to be the what? Therefore, the theoretical yield is 52.8 kilograms. Okay, so you can write it like this or write it like that if it's the fill in the blank problem. If it's a multiple choice, you have to find the one that matches. So far I have answered by saying which formula is the limiting reagent, the one that makes less product, and I've said how much of the product is actually made, this amount here or this amount. Okay, so let me go back and see what the questions were. Limiting reagent, I got that one here. Theoretical yield, I got that one there. Then our last move is percent yield. Okay, so percent yield, this one is the actual yield over theoretical yield, okay, times 100. So for this one, oh, I do have space. Percent yield, what's my actual yield? The one that they said I made. Oh, this is where this number comes in. So you, once again, here you can use the top number or the bottom number, whichever works. Let me go ahead and I guess I'll use the top number, 42800. I'll say 42800. If I use grams of titanium, I have to divide by this amount here, 52810 grams of titanium. Okay, so they're saying that I should have been able to make this amount, but I only made this amount. Okay, expected. This is what actually happened. Okay, so what actually happened is less than what was expected, times 100. Let's see what we're doing in percentages. So it's 42800 divided by 52810. Okay, so I'll say 81% is not that bad, right? But when you're working for a company and the percent profit, when the percent of the money they make depends on how much product you make, there is 19% of product that you didn't make that you should have been able to make, right? So I've heard people who, I didn't work in industry that long. Sadly, my career in industry wasn't long as I wanted to be. Okay. But I've heard like it's very cutthroat. People are like, which kind of makes sense because the company wants to make profit. They're not a charity organization. So this is where they work it out to show you what they got. And this is what they got in the end. I'm seeing some typos. When they write grams here, they mean kilograms. Okay. But you end up with 80.9%. Okay. So I'm not going to work on that one. Let's see. Okay. So we've talked about all of this stuff here. I don't want to define that again. I want to work on this last problem here. This is calculating the mass. Oh, okay. This problem looks like the one that we just worked on, doesn't it? It really does. So they're adding a little subsection here after we've done everything. Recall further that in the reaction mixture containing this right here and this, TiO2 was the limiting reactant. Yes, that's what we got. Now they want you to calculate the mass of the reactant in excess, which is carbon, that remains after the reaction has gone to completion. Ooh. So they want us to add this little subsection to that question. Let me go ahead and copy it. So I'm going to add here. There's a fourth goal. Copy. And because I'm trying to be somewhat, not really lazy, but resourceful, I'm going to do that right here. Yeah, I do apologize for all the background noise. There's something happening in the streets, and it involves a lot of fire brigades and sirens and stuff. Okay, We're trying to calculate the mass of the reactant in excess. So here's the thing. We got the percent yield. We did all that work. Okay. So what I'm needing here, what I'm needing to actually do my work, I'm going to need the balance equation like I had. Then I'm going to need these right here. So let me start with the things I need. For one, I need my balance. Oops, what am I doing? I'm trying to get this copied out. I need my balance equation. Copy. Okay, so I'm going to copy this. I need that right here. Okay. There's, yeah, what's happening outside is really distracting me. Sorry. So I got this right here. Now I need they did say what? 88.228. 8.6. This is kilogram and this is kilogram, right? This is my given 1 and this is my given 2. Okay. And then my actual yield was given to me here. I've already forgotten what that was. 42.8. 42.8. This is kilograms. Okay. So I'm kind of starting from this part here. Now I want these numbers as usual in grams. So 88200 grams, 28600 grams. Okay. Because the conversions that we do don't work with kilograms, they work with grams. Okay. To determine amount of excess reagent left over, comma, we need to calculate amount of excess reagent needed. Okay. So remember how I was talking to you about buying the food that's prepackaged food where everything is measured so you have no excess, no leftover? We're trying to figure out how much would we have needed to avoid having any excess. So this is our first goal. We're going to figure out how much did we actually need of the excess reagent, which we have decided that limiting reagent is titanium 4 oxide. The excess reagent, which I'm labeling as ER, is carbon. So how much of the carbon did we actually need, right? The way the stoichiometry works here, whatever we need, whatever we're looking for is labeled our wanted. So since we're trying to figure out how much of the excess reagent is needed, we are actually going to make this the wanted, because the wanted symbol or the wanted that we assign is the one that we literally want information on. We're trying to figure out how much of the excess reagent did we need from what was available if all of the titanium 4 oxide reacted. So this would be our wanted, and then this will be our given. So I'm going to do one more mass to mass conversion. So in my mass to mass conversion, as I'm writing here, perform. Okay, I don't smell any smoke. For real, all these sirens, I'm thinking, is there a building burning and I'm sitting here casually teaching when I should be running, heading for the streets? I don't smell anything. Sorry, guys, I'm getting a little paranoid. It's just there's so many sirens out there. Okay, perform mass to mass. No, if something was going on, I'll hear the alarm. Perform mass to mass. Okay, in the mass to mass, we'll start with our excess reagent, and this will be labeled as our given. And then we'll go to our limiting reagent, and this will be our wanted. So I'm going to do this last pass right here. Let me label it a different color. How about purple? From here to here, because what we are landing on is what we're trying to figure out. So do I have these masses? Yes, I do. I'll use, this is my starting mass, 8 0.8200 gram of TiO2. Okay. PT, gram of TiO2. I like this last one because I don't have to do a lot of math. Let me just go back here and not really cheat, help myself. I need this number here because I already have the work done. 80 gram of TiO2, 1 mole of TiO2. Okay. Then BE. In the balanced equation, I need to relate TiO2 to carbon. So TiO2 is 1 mole from the balanced equation. Carbons, I saw 2 moles. 2 moles of carbon. Okay, done. Next, 1 mole of carbon. Carbon is just 12 grams of carbon. That's it. So what we're saying here is if all 88200 grams of titanium 4 oxide react, how much of the carbon do we actually need as a compatible partner? Well, we're about to figure this out. Let me do the math. 88200 times 2 times 12 divided by 80. I end up with 26460 grams of carbon. Okay, if that's what we need, what did they actually give us though? No, this came in the wrong place. Add a page right here. Come on. Add a page right here. Okay, they're saying we only need 226,460 grams of carbon. But how much did they actually tell us we had? 28. Okay. So 488.2 kilograms. I'm going to go back to the kilogram mode of titanium 4 oxide to completely react, comma, we needed only 26.5 kilograms of carbon. So I just converted this number to kilograms, 26.5 kilograms. That's all we needed. But they gave us how much? 28.6 kilograms of carbon. What a waste, right? So how much do we have in excess? So the excess amount of carbon is equal to 28 points. Ooh, where'd the 2 go? Come on, work with me here. 28.6 kilogram minus 26.5 kilogram, which is going to be 28.6 minus 26.5, 2.1 kilogram. Imagine, that's a lot of mass of carbon is in excess. Now, if you're in a company situation, you don't want to be wasting kilograms worth of chemicals. Is a lot of money. This is a waste. If possible, I mean, depending on what you're trying to do, of course, but yeah, that's a lot more chemicals than what was needed. Way more, right? So they work it out here. Once again, oh, sorry. I realized I just added all these pages because I clicked on the wrong button. It's a struggle. It's real. Yeah, they did the work way down here, right? Once they brought in that, they did the work on the bottom, and they were able to figure out. Now I can't see it, that question. They were able to figure out how much. Oh, there it is. Yeah, here's the question. They were able to figure out how much of the titanium was in excess. They do all the work here. So feel free in your own time. There it is. Okay. I'm trying to go through the math, so it's not just math. You're understanding the purpose, because remember, when you see this in a comprehensive setting, you want to be able to survive the overwhelming number of information you're going to be having, right? And if you understand the information in context, to me, at least that's what helped. That meant I would be studying a lot. I spent a lot of my time in the library. It looked like I worked there. No, I didn't work there. I didn't work there. Do you work here, ma'am? No, I don't. Okay. I don't know what's up with this page. There's a question missing here, but I did talk about the different types of reactions. So I'm just going to go through and mention real quick. This is combustion, right? You have compound, element, compound, compound. And let's see. Oh, here they ask you to complete the equation and balance it. So let me go ahead and work that part out. I'm skimming over this part real quick because I've already discussed the types of reactions. If they say complete and balance a combustion reaction, right? Combustion, you know that this is going to be your fuel. Combustion reactions always have oxygen. And then since you have this chemical here has the following ingredients. You have some carbon, a certain amount, X. You have some hydrogen, a certain amount, Y. You have some oxygen, a certain amount, Z. I'm just keeping this generic. Since you have this combination, not really, yeah, not the order, but a combination of elements, then you're going to make carbon dioxide and water. If you have carbon, hydrogen, and oxygen, or carbon and hydrogen in your compound, you make carbon dioxide and water with a combustion reaction. Then you have to balance it. So let's balance this. Carbon, hydrogen, oxygen, oxygen, oxygen. Let me do carbon first. I don't know what I'm doing. I get there. Carbon, oxygen, hydrogen, oxygen. Man, there's oxygens everywhere, right? We're definitely dealing with that one last. Okay, let's see. Carbon here in this formula above, I only have 1 carbons. I have 3 plus 1. I have 4 oxygens. I have 1 oxygen here. Here I have 2 oxygens. On the right, I have 1 carbon. I have 2 oxygens. And I have 2 hydrogens, and then I have 1 oxygen. Okay, let's see. The carbons from left to right seem the same, right? 1 carbon, 1 carbon. I have 4 hydrogens here. I have 2 hydrogens here. I want to make them equal. So times 2 to get 4, times 2 to get 2. Okay, so far it appears that my hydrogens are balanced. But in the process, I have messed up the oxygen because now I have a total of 4 oxygens, right, when I add these two. But then over here, I have a total of 3 oxygens. So we got a problem, right? This number here is an odd number, so maybe we should double it. Yeah, this is one of those questions where it's not as simple as it appears. Let me try to make this an even number and see if that will work. So if I double this and double this and double this in an effort to make this oxygen here an even number, does it work out? Let's see. If I double the carbon, I get 2. If I double this, I get what? 8. If I double this oxygen, I get 2. But now we have even numbers. So now let's see how we can approach the left. Okay. Here I have 2 hydrogen. Here I have 1 oxygen. Okay, in order to make the hydrogen on the right 8, I have to multiply by 4. Okay. That makes it 8. And then the hydrogen again looks balanced, right? And then because in the same formula, in the same compound, I put 4 here, and this is going to be 4. So now let me see. Oh, the hydrogens look balanced, but then the carbons are now off, right? So times 2 to make 2, to match this to this. But then the same formula, so I have to multiply this oxygen here by 2, and we end up with 4. 4 plus 4, we end up with the oxygen total of 8. So it looks like the hydrogen is balanced, right? The carbon is balanced. Our only issue is the oxygen. Oh, this is good. On the right, I have 8 oxygen. Here, I have 2. I just need to make the 6. I multiply by 3 to make it 6. Then when I add these 2, I end up with a total of 8. Right? Yeah, with balancing, I shouldn't say you kind of have to be patient. And just you kind of, it's kind of, somebody says it's like accounting. I say not. I took accounting class and I got a D in that class. I'm just trying to figure it out. I'm trying to make a comeback, okay? And it's been years. I decided to challenge myself one of these days to take an accounting class. I have to be in a good space emotionally because the last time I took accounting, I got a D. So they say balancing equation is like accounting. I'm like, yeah, right. I did not get the logic in accounting at all. But you're trying to, I get what they're trying to say. It's like you're trying to make things work out. You're moving numbers here and there to make things work out. So I get what they mean. But in my experience, they were not similar. Okay, let's balance the equation. Move the multiplier up, move the multiplier up, move the multiplier up, move this multiplier up. Oh, I wish accounting was that simple. I mean, probably an accounting major would be like, no, chemistry is not simple. I get the logic of chemistry. I've spent years investing in this, right? All you're seeing right now is the dividends and growth. I look over this material before I show up. I don't just show up like, just show up. But yeah. So yeah, that's how I balance the equation and I get what they get. So here they're once again showing you how to complete the chemical reaction. So I'm going to judge this reaction type. The metal here is just an element. X2 is a diatomic nonmetal, also an element. So this type of reaction here is a combination reaction. We talked about this before. When you have an element adding to an element to make a compound, that's a combination reaction. So you're going to ionize, right? Na will become Na plus, Cl will become Cl minus. Crisscross these and you're crisscrossing just the charge and neutralizing and you get NaCl, and then you complete the reaction and then you balance it. Over here, this reaction they're showing you here, this reaction is metal plus water. So metal is an element because it's a metal by itself. Water is a compound, so you're making a metal and a water. And then here, it's hard to tell, but these two combined make a compound, and then this one here is an element. So this would be a single displacement. Okay. And so this kind of goes through the rest of the reaction here, so I won't really do that part here much. What I want to do is quickly introduce the next chapter, but we're going to be going over this next. We're going to be going over solution chemistry, where we deal with, I mean, you can see we have a lot of slides, so we won't make much of a dent today. But we're going to be dealing with reactions as far as solutions is concerned. So I want to go ahead and talk about what a solution is real quick before I let you go. A solution is what is made when you have a mixture. Okay? So a solution may or may not be a chemical reaction. The bottom line is you have to have a mixture, and it has to look uniform. So when it says here homogeneous, it means it's uniform. In a solution, you have a solute and a solvent. Okay? So you add these two reactants that are labeled a solute and a solvent, and you end up with a solution, which is a mixture. They tell you the solute is the amount you have lesser amount, then the solvent is the one that you have greater amount. Okay, so the example they gave you here is table salt mixed with water. If you're trying to make salty water, usually you take some salt and the salt will be the solute, and then the solvent will be the water. So for the most part, the water is the greater amount. Okay, so they show you here in the lab making a solution. Solutions in the lab are usually made in certain containers, right? There's certain approved containers and the other ones are frowned upon, right? Yeah, so it's like when you're trying to make a solution, you make it in the volumetric flask. The volumetric flask, like this one here, was designed to make solutions in. So it has a mark on top here. When you grab this flask, it's flat on the bottom, and depending on the amount of liquid or solution you're trying to make, you will grab an appropriate size. So let me see what they're trying to make here. Oh, they're trying to make 1 liter. So 1 liter here will be the same as 1,000 milliliter. So when you go to the lab, it will be a huge, kind of long flask. It'll be labeled either 1,000 milliliter or 1 liter, most likely 1000 milliliter. But you will grab it, and it shows you here that a specified amount of table salt was measured, and then it was poured into the flask using this funnel as an aid. And then once it was poured, then water was poured in after the fact to add to the flask. Then you cover this with your thumb because the chemical here is safe. This is the old school way. Or if you're doing the same process in organic chemistry where the chemicals are more dangerous, you don't use your thumb. You use a cling film, which is like, I'm saying cling film. Cling film is what we call it in the kitchen, right? It's a paper kind of like the cling film paper, and you cover this, or the container comes with its own stopper. You can stopper it, secure the stopper with your thumb because it doesn't stopper it, like it sits on it, but it doesn't really anchor there completely. You put your thumb over this. So imagine this is a thumb, and your hand is here. I'm not the best drawer artist. I'm about to say drawer. This is it. Yeah. Okay. This is supposed to be your thumb. I'm laughing because when I was a kid, delusions are real. I thought I was a good artist. Now I'm like, how did I think I was a good artist? I never did practice though, to be honest. Never did. When I realized I wasn't a very good artist, I just stopped practicing and I focused on learning math and science as a good African kid. Anyway, your thumbs are here. I mean, your fingers are here. Then your thumb goes over this. So something like this, right? And then your hand is like that. Oh, this is a little better. So you hold it on your right that, and then tip it over and shake it. So you don't see my hand right now, but you tip it over and shake it, and then that dissolves all the salt in the water, and it looks like water, like a little bit murky. But what you form here is a solution. And so depending on the amount of solute you use, you can make a dilute solution where you use less solute, or you can make a concentrated solution where you use more solute. Okay, so you want to be aware, less solute, more solute. Okay, so what I'm going to do is I'm going to just end here because I can't really go into the rest of this without really, I'd rather just go over, I'll just say start here next time. I'll write myself a note. Show, what's that called? Particulate diagrams. Particulate diagrams of dilute versus concentrated. No, say start here. Okay. So this is a note to myself. When we start, I want to show you how a dilute solution is presented versus a concentrated solution. How can you tell one from the other? If you were asked to explain it at a particular level, how do you do that? How do you do how do you use those model diagrams to explain the difference? Okay. So yeah, we're gonna end here. Do you have any questions about anything else? Not really anything else, but just anything. If not, this is all I have for today. Yeah. And so, yeah, I guess today's Wednesday, right? So we'll meet next week for the rest of this chapter. Okay, so I am going to sign off. Okay, you're welcome. Have a nice weekend. I know it's just Wednesday.